This is video 24.2, second video for chapter 24 on magnets. This is covering pages 462 to 466. So what actually makes magnetic force? So we talked about how charged particles have an electrical force, and if they're moving, then they have a magnetic force as well, because it's the motion of the electrons that are in each atom that cause it to be magnetic. But if that were the case, since electrons are constantly moving, then everything would be magnetic, and clearly everything is not magnetic. So what they really think is happening is down at the atomic level, there are certain materials where their electrons spin in unison and they match and they all line up in the same direction, and that causes them to be more magnetic. Iron in general tends to be very much more magnetic, and if it's slightly unmagnetic, if you have like an iron nail, you can cause it to be magnetic because you can encourage those atoms to line up and get in formation. So a normal piece of iron might have the little atoms, and we're going to call them domains. The little domains might line up like this, where they're kind of all over the place. They don't match. They don't go in the same direction. This would be like a normal unmagnetized nail, for instance. So if we can get those domains to line up so that they're all facing the same direction, since each atom is a magnet, if we can get them lined up, then their forces are going to combine and create a magnetic structure inside the iron. So a magnetic domain is going to be a cluster of aligned atoms, and the more aligned the domains are, the stronger the iron magnet. So the one there on the left isn't going to be strong at all if it's magnetized even at all. But if you can get them to line up and all face the same direction, then now you can create a magnet, and you can create a strong magnet. Now if you take a normal nail, you can turn it into a magnet. There's a couple different ways. First of all, you can bring a magnet to it. You've probably seen this before. If you have a magnet and you pick up, say, a paper clip, then you can pick up another paper clip by just touching it to the paper clip that is attached to the magnet, because once it attaches to the magnet, it lines up all of those domains inside your paper clip to cause them to become magnetized. This is a very temporary effect. Once the paper clip has been removed from the magnet, that paper clip is no longer a magnet itself. If you bring it closer to a strong magnet, so you can have a weak magnet, can cause it to be magnetized. If you bring it near a stronger magnet, then the effect might last slightly longer. Or if you leave it attached to it for a longer amount of time, you can create a magnet out of an unmagnetized piece of metal. Now, if you bring a magnet near your unmagnetized iron nail and not touching it, just close to it, so that you can get it to line up with the field lines, the magnetic field lines that are in that magnet, you can get those atoms to kind of line up with it, and then you just kind of tap it gently with a hammer. We're talking gently, not hard. You can rearrange some of those domains to get them to line up. If you do this, it's possible to make a permanent magnet by doing that. And then the fourth way would be to use a magnet and to, in the same direction constantly, be stroking your iron nail in order to make a permanent magnet. So that's 4 ways you can take something that is not magnetized and make it magnetized. Now there are certain substances that, because of their atoms and the electron spin, they're always going to cancel out and they'll never be magnetized. But most metals have a tendency to be able to be magnetized at least a little bit. If you were to take a compass and walk around your house, there are certain things where if they've been stayed in the same place, they may become slightly magnetized. Now, not strong enough to be able to stick them to your refrigerator or for other things to stick to them, but they can become slightly magnetized. You could check that with a compass, the way we did with the magnetic fields on the magnets in class. So like I said at the beginning of the last video, there was a guy who was trying to demonstrate something with magnetic fields, and he noticed that an electric current created a magnetic field. So if a moving charge produces a magnetic field, then by definition, what a moving charge are currents. So currents can also produce a magnetic field. So when the electricity is flowing through a wire going through any electrical device, there's a magnetic field that is produced around it. And if there's a magnetic field produced around it, then that's something that we could measure with, at least with a compass. So if you take a coil of wire that is carrying a current, the conditions are just right, you can turn that into an electromagnet. So that is going to be a magnet that is stronger than a normal magnet because it is using current in order to create your magnetic field. This is often used at like junkyards. They can take and pick up large vehicles and move them around by use of an electromagnet on the end of their crane. So there's a couple ways you can do to increase your strength of your electromagnet. So first of all, you can make current flow through more. So more current, less resistance is going to give you a stronger magnet. A lot of them will use an iron core. That iron core increases the magnet. You're basically making a magnet on the inside there, and then all together they add up and their forces add up and create a stronger magnet. And then sometimes you can use a superconductor for the coil. So remember, a superconductor has very little resistance. So if that's the case, then you have a lot of current and it's not going to slow down by getting resisted by the wire. So that can create a stronger electromagnet. So the reason that this would be used is because large currents will flow through the wire very easily. So what do we use superconducting electromagnets for? One of the uses for them is in particle accelerators. So they can be used to guide the particles around the accelerator. So the one that is the Fermi National Accelerator Laboratory, their particle accelerator is 4 miles around, and so they use these magnets to help guide the particles that are being shot through the particle accelerator. Anytime you've gone to get an MRI, they are using electromagnets in there to get a view of inside your body. If you've ever gone to get one of these, they try to make sure that there is no metal in your body. You don't have any jewelry on. You don't have any metal plates or screws or anything like that, because it can cause a lot of damage to your body if you have metal inside you, if they're going to be using the magnets. And then another one that is coming up that's not really high use. There have been that are built, but they're very expensive. Way to travel would be maglev trains. So if you take, basically they use the superconducting coils underside of the train to create they take the aluminum shell track that they run on and they make it become a magnet so that it is repelling the train upward by use of the superconducting electromagnet, so that the train will hover just above the track just a little bit. And so because you've reduced that friction there, the train can go much faster. So the one that they built in Shanghai operates between, I'm trying to remember, like the airport and downtown, travels pretty far, and it can get up to speeds of 460 kilometers per hour. So there's like 30 kilometers that it covers, and it can make that trip in 8 minutes. So because it is not riding on the rail and you're not feeling the friction of that, the passengers don't feel it as much as if you were trying to drive that fast in a normal train. You would feel it a lot, lots of bumps and bouncing all around. Now, one of the things that prevents it from going any faster than that, then you've got some air resistance, so they are generally very slopey looking in the front, so that you've got good aerodynamics. And then also because the comfort of the passengers on the train, they don't really want to be going that fast, so they slow it down a little bit just for the safety of their passengers. All right, go ahead and click on the link and complete the quiz. This is over yesterday's video and today, so you'll need both notes in order to take the quiz, and I'll see you in class.